everyone, thank you for watching this video. So as you can see, I have a 3 by 3 matrix right now, and we know it's a 3 by 3 because we make that L. We got 1, 2, 3 by 1, 2, 3. Okay, so last time we did the 2 by 2 matrices, and you should all remember how to do that, and if you don't, you can look back in your notes, and there is going to be a little reminder at the next video that you're going to watch. But for organizational purposes, it's very important when we're doing 3 by 3 matrices. We really need to make sure that we have the system down, the process down, so that we're not forgetting how to do it. So this is my matrix A. When I want to write the determinant for it, remember we can just do det of A is equal to. Now, this is the tricky part. So we're going to be multiplying by a constant, which is our A, B, C, or D, 3 times. So we're going to put, first one, we're going to have our A right there. Then I'm going to make a 2 by 2 matrix. But what do we put in this 2 by 2 matrix? So here's a trick. So you have A, B, C, and we're going to always be using these to multiply by a constant. So cross that out. Now, A is right here. So I'm going to cross out this, which just leaves E, F, H, I. So I put E, F, H, I right there. Now, we put minus. Always. Even if B is negative, it's always a good idea just to put, let's say it's -2. We put minus, and then we do another -2. We know 2 negatives make a positive, so plus positive. So then you don't have to worry about that. Always make sure you put this negative right here. If you don't, it's going to mess up your entire determinant. So then I'm going to write my B. Then I'm going to do another 2 by 2 matrix. Now, if we're going to be doing the same thing we did with A, what section do you think I should cross out? If you said EH, you're correct. We're going to go like this. So this is gone. So we have D, F, G, and I. So let's write that. D, F, G, and I. Now for C, just plus C, the 2 by 2 matrix. Okay, so if it's plus C, what do we need to put? What 2 by 2 matrix do we need to place right there? If you said we cross out Fi, so we have D, E, G, H, you are correct. D, E, G, H. So this is the setup to do a 3 by 3 determinant, but we still have a matrix going on. So for a recap, let's think about a 2 by 2 matrix. What do I do now? Okay, let's think about that. If you haven't, let's look in our notes and let's figure out what you need to do, because that will tell you how to solve for this.
In the last video, we defined the notion of a determinant of a 2 by 2 matrix. So if I have some matrix, let's just call it B. If my matrix B looks like this, if its entries are A, B, C, D, we defined the determinant of B. The determinant of B, which could also be written as B with these lines around it, which could also be written as the entries of the matrix with those lines around it, A, B, C, D. And I don't want you to get these confused. This is the matrix when you have the brackets. This is the determinant of the matrix when you just have these straight lines. And this, by definition, was equal to AD minus BC. And you saw in the last video, or maybe you saw in the last video, what the motivation for this came from. When we figured out the inverse of B, we determined that it was equal to, the inverse of B was equal to 1 over AD minus BC times another matrix, which was essentially these two entries swapped. So you got a D and an A. And then these two entries made negative, so minus C and minus B. this was the inverse of B. And we said, well, when is this defined? This is defined as long as this character right here does not equal 0. So we said, hey, this looks pretty important. Let's call this thing right there the determinant. Let's call this right here the determinant. The determinant. And then we could say that B is invertible if and only if the determinant of B does not equal 0. Because if it equals 0, then this formula for your inverse won't be well defined. We just got this from our technique of creating an augmented matrix, whatnot. But the big takeaway is we defined this notion of a determinant for a 2 by 2 matrix. Now, the next question is, well, that's just a 2 by 2. Everything we do in linear algebra, we like to generalize it to higher numbers of rows and columns. So the next step, at least, let's just do baby steps. Let's start with a 3 by 3. Let's define what its determinant is. So let me construct a 3 by 3 matrix here. Let's say my matrix A is equal to, let me just write its entries. First row, first column, first row, second column, first row, third column. Then you have A21, A22, A23, and you have A31, third row, first column, A32, and then A33. That is a 3 by 3 matrix, right? Clearly, 3 rows and 3 columns. This is 3 by 3. I am going to define the determinant of A. So this is a definition. I'm going to define the determinant of this 3 by 3 matrix A as being equal to, and this is a little bit convoluted, but you'll get the hang of it eventually. In the next several videos, we're just going to do a ton of determinants, so it just becomes a bit of second nature to you. It's a little computationally intensive sometimes, but it equals this first row. It equals A11 times the determinant of the matrix you get if you get rid of this guy's column and row. So if you get rid of this guy's column and row, you're left with this matrix here. So times the determinant of the matrix A22, A23, A32, and then A33, just like that. So that's our first entry, and that's a plus this. And then I said it's a plus this because the next entry is going to be a minus. You have a minus this guy right here. So then you're going to have minus A12 times the matrix you get if you eliminate his column and his row. So times, you're going to get these entries right there. So A21, A21, A23, A23, A31, A31, and then you have A33, A33. We're not quite done. You could probably guess what the next one's going to be. And you're going to have a plus. Plus, let me switch to a better color. Plus this guy. Plus A13 times the determinant of its, I guess you could call it its submatrix. We'll call it that for now. So this matrix right here. So A21, A21, A22, A31, A32. This is our definition of the determinant of a 3 by 3 matrix. And the motivation is because when you take the determinant of a 3 by 3, it turns out, I haven't shown it to you yet, that the property is the same. That if the determinant of this is 0, you will not be able to find an inverse. And when I define determinant in this way, if the determinant does not equal 0, you will be able to find an inverse. So that's where this came from. And I haven't shown you that yet, and I might not show you because it's super computationally. It'll take a long time. It'll be very hairy, and I'll make careless mistakes. But the motivation comes from the exact same place as the 2 by 2 version. But I think what you probably want to see right now is at least just this thing applied to an actual matrix, because this looks all abstract right now. But if we do it with an actual matrix, you'll actually see it's not too bad. So let's leave the definition up there, and let's say that I have the matrix. I have the matrix 1, 2, 4, 2, 2, minus 1, 3, and 4, 0, 1. So by our definition of a determinant, the determinant of this guy right here, the determinant of this guy, so let's say I call that matrix, let's call that C. C is equal to that. So if we want to figure out the determinant of C, the determinant of C is equal to, I take this guy right here, so let me take that, 1 times the determinant of, let's just call it this submatrix right here. So we have a -1, -1. We have a, we have a -1. Got to be careful. We have a 3. We have a 0. And we have a 1. Just like that. Notice I got rid of this guy's column and this guy's row, and I was just left with -1, 3, 0, 1. -1, 3, 0, and 1. Next, I take this guy. And this is the trick. You have to alternate signs. If you start with a positive here, this next one's going to be a minus. So you're going to have -2 times the submatrix, we can call it, if we get rid of this guy's column and this guy's row. So 2, 3, 4, 1. So 2, 3, 4, 1. I just blanked this out. If I could videotape my finger, I would cover my finger over this column right here and over that row, and you would just see a 2, a 3, a 4, and a 1. And that's what I put right there. And then finally, we'll have plus. We went plus, minus, plus. So finally, we'll have plus 4 times the determinant of the submatrix if you get rid of that row and that column. So 2 minus 1, 4, 0. 2 minus 1, 4, and 0. Now these are pretty straightforward. These are not too bad to compute. Let's actually do it. So this is going to be equal to 1 times what? -1 times 1. Let me just write it out. -1 times 1 minus 0 times 3. This just comes from the definition of a 2 by 2 determinant. We've already defined that. And then we're going to have a -2 times 2 times 1, 2 times 1, minus 4 times 3. And then finally, we're going to have a plus 4 times 2 times 0, 2 times 0, minus -1 times 4. Minus 1 times 4. I wrote it all out so you can see that these are just, this thing right here is just this thing right here. And then you have the 4 out front. This thing right here was just this thing right here. It's just the determinant of the 2 by 2 submatrix for each of these guys. And if we compute this, this is equal to, see, -1 times 1 is -1, minus 0, that's 0. So this is a -1 times 1, so that's a -1. And then we get, what is this equal to? This right here is 12. So you get 2 minus 12, right? You get 2 times 1 minus 4 times 3. 2 times, so it's -10. So that is equal to -10. And then you have a -10 times a -2. So that becomes a +20, right? -2 times -10. And then finally in the green, we have 2 times 0. That's just a 0. And then you have -1 times 4, which is -4. But then you have a minus sign here, so it's +4. And then 4, so this all becomes a +4. +4 times 4 is 16. So plus 16. And what do we get when we add this up? We get 20 plus 16 minus 1. It is equal to 35. And we're done. We found the determinant of our 3 by 3 matrix. Not too bad. Not too bad right there. So that is equal to the determinant of C. So the fact that this isn't 0 tells you that C is invertible. So we know that C is invertible. In the next video, we'll try to extend this to n by n square matrices.